You've probably already used or come across a QR code, whether it's at the bottom of your TV screen, on a store window, on a product, or even printed on a restaurant or bar table. And all you have to do is point your smartphone camera at it, and it quickly scans it, allowing you to click and be redirected to the link hidden in the code. And you've probably seen other QR codes like these too, right? They're all QR codes, aren't they? Actually, no, only this one is a QR code. We'll look at the others later on. But why were QR codes created, and how do they actually work? Let's start with a simple situation. Imagine that you need to access the following link, https://w.youtube.com. Although the link is short, when typing it, the chances of making a mistake are huge, especially if we're typing it in a hurry, afraid that it might disappear at any moment. But by pointing your smartphone camera at the corresponding QR code link, things get much easier and we can instantly access the website. And that's the idea behind QR codes, to store data, web address links, images, texts, phone contacts, email addresses, videos, and more in a small coded image that can be easily and quickly read. And it is considered an evolution of the barcodes currently used for product identification all over the world. While barcodes are 1D codes, that is, one-dimensional codes that can only be read horizontally by a laser, QR codes are 2D codes, that is, two-dimensional codes, and they are read both horizontally and vertically by a camera and can store much more information compared to barcodes. While a regular barcode can contain between 8 and 25 characters of information, a regular QR code can store between 40 and 127 characters of information. And QR stands for Quick Response, meaning a quick response code. That's because it can be read in just under 3 seconds. And there are several versions of QR codes, 40 to be more precise, and the size of the code for each version will be equal to the version times 4 plus 17. In other words, in version 1, the size is 21 by 21 modules, and in version 40, it's 177 by 177 modules. But after all, how do they work? Although at first glance a QR code may seem like a complete mess and total disorder that doesn't convey any information to us, it's possible to decode it just by analyzing it. In every QR code, there will be these 3 squares, 2 at the top and 1 in the bottom left corner. These are called finder patterns, and they serve to show the camera the code's orientation. That is, whether it is upside down or sideways. There's a 4th small square in the bottom right corner. This is called the alignment pattern, and it allows the code to be read even if it is at an angle on a curved surface or distorted by perspective. But before we continue, we need to understand the basic principle of how computers handle information. Computers only understand zeros and ones, and all the information that is put into them, from numbers to huge texts, is transformed into zeros and ones. And each letter, number, or symbol has its equivalent representation in binary form, that is, in zeros and ones, with 0 being the absence of information and 1 being the presence of information. In the QR code, the white spaces are interpreted as zeros and the black ones as ones. The stored information starts from the bottom right corner and goes up. It curves, goes down again and again until it reaches this point. Right at the beginning of the code, in this area, which is made up of a group of 4 modules, it contains information about the encoding mode used for the information. In other words, what kind of information is in the code, which can be numeric, alphanumeric, meaning numbers and letters, bytes, or bits, and kanji, which is the Japanese alphabet. With 4 in this space, each indicates a type of data present in the code. Next, we have the character count indicator, which is a rectangle formed by 8 modules that indicate how many characters the entire message or the entire code contains. Since there are 8 spaces, each one will represent a specific number, in this order: 1, 2, 4, 8, 16, 32, 64, 128, and you must be wondering what the logic behind this order is. With these numbers, you can represent any number from 0 to 255. The number 0 is represented with all the modules white, that is, the absence of information. So if the message contains a character, only the module corresponding to 1 will be black. If the message contains 5 characters, only the modules corresponding to 1 and 4 will be black. And if the message contains 15 characters, only modules 1, 2, 4, and 8 will be black, and so on. And if all of them are black, this will correspond to the number 255, 255. In the following set, which is also made up of 8 modules, the actual information or message that was encoded in the QR code begins, and it is read in this zigzag sequence until it reaches this group of 4 modules, which indicates the end of the message. And if you pay close attention, you can see exactly what was encoded in this QR code, www.wikipedia.org. Okay, but how does this bunch of black and white dots translate into letters, numbers, and symbols? To understand this, we need to know the ASCII table, which is a system for representing letters, numbers, and punctuation marks in binary form, that is, zeros and ones. So according to the ASCII table, the lowercase w corresponds to the number 119 in decimal form. And according to our QR code system, to represent this w, the numbers 64, 64, 32, 16, 42, and 1 must be marked. That is, they will become black dots, which mean 1 and the numbers 128, and 8 will be white dots, which means 0. And the result of this will be a lowercase w. And the computer interprets this in milliseconds, and the reading keeps following the same logic until it reaches the end. So in a QR code, only this area actually contains the information itself, but what about the rest of the code? What's in it? Right after that is the end of the message. The error correction information starts, which is the part that contains information responsible for error correction, and it is read from top to bottom until it gets here. Then it continues in E4 in a zigzag sequence until it reaches E7. The way the codes in this part work is really crazy, and they use a mathematical method called Reed-Solomon error correction. But basically, it allows the QR code to still be read, even if one or multiple parts of the code are missing, covered, or damaged. For example, if a part that contains the information is damaged, it's possible to use any of the correction code blocks to replace that part. And the amazing thing is that even if several of the error correction blocks are damaged, as well as the message itself, it's still possible to use the remaining blocks to reconstruct the message. And it's thanks to this that we see some QR codes containing icons, emojis, or even brand logos right in the middle of them. That's because Reed-Solomon error correction will be able to replace that part, and the code will still be readable. And this Reed-Solomon code is used in music, on CDs, and in various fields, but it was originally developed for satellites and space probes. Now that we know the basics, there are other more complex parameters that occur in QR codes. For example, the way some of the modules are read can be inverted or swapped in certain situations, both in the direction in which the code is being read. In larger codes, some of the modules may have different sizes and shapes. There are also the mask patterns, 8 in total, which are used to change the position of the bits or the black dots in the resulting QR code. It's complicated, but basically it helps in situations where the reader might have trouble interpreting areas with large white or black spaces, or areas that look like the alignment pattern but actually aren't. So depending on the mask used, it inverts some dots, breaking up these areas and making it easier to read. Keep in mind the computer reads all this in milliseconds. But there is more data in QR codes like these zones, which contain what's called format info, which holds data about the error correction level used in these modules we saw earlier. This data is stored in these two modules in both positions. These levels can be low, medium, quartile, and high, and each corresponds to how much information can be recovered. The next three modules contain data about the type of mask used, and the remaining ones contain data about the format error correction. There is also this black dot exactly in this position, whose real function is not known. And in this part, there is the timing pattern, which is made up of horizontal and vertical lines. These lines show the reader the QR code's version and its size or density, and there is also this large white border on the outside of the entire code, which marks the end of the code and helps to distinguish it from other things that may be around the code. Okay, now that we know how they work, how much information actually fits in a QR code? In version 1, it can hold about 17 characters of information, while in version 40, it can hold 4,296 alphanumeric characters, or approximately 1.5 full word pages. Just so we have an idea of how much information that is, it takes up 2,953 bytes of storage space, or about 2.88 kilobytes. For example, this Windows 10 sound is under half a second long, is 11 kilobytes. But there are other codes that are very similar to QR codes, and you may have mistaken them for QR codes before. Like the JSTEC code, which looks a lot like QR codes and is used on train tickets in Europe. The data matrix code, which is very common in electronics for identification, like RAM memory chips and others. The PDF 417, which looks a lot like barcodes but is used on airline tickets by airlines, on personal documents, and so on. And there are many others like the SHOT code, which is circular, the JAB code, which uses colored dots to store information. The high-capacity color barcode, created by Microsoft, uses colored triangles to store information, the MAX code, and many others.